welcome everybody to the Latin American webinars of physics. Today we are again here in this stage for listening a very interesting webinars. This time we have Fabian Bautista from the Institut de Physique Théorique in Saclay, France. So first of all, Fabian, he obtained his PhD from the Perimeter Institute in 2022, and after that he is postdoc at the Institute of Theoretical Physics in Saclay, as I said before, and he specializes in deriving classical observables in gauge theory and gravity using scattering amplitude with focus on spin effects, Cuban interactions, and wave scattering, classical electron dynamics, and gravity. So Fabian, welcome to lawphysics. It's very nice to have you here, and you can start whenever you feel to.
Yeah, thanks. Thank you, Roberto, for the introduction, and thank you for the invitation. So let me share my screen so that we are all on the same page. So let me know if you can see my screen.
Yes, we can see
it. Awesome. Okay, so thanks a lot. So today I'm going to be telling you a little bit about the new approaches that the scattering amplitudes community has taken the last decade to start thinking problems besides particle physics, also how to apply the modern scattering amplitude techniques to recent problems in gravity, in particular the binary black hole problem. So, and I like very much the slide that you guys prepared for the announcement of the talk, so that I also borrow it to be the front of my presentation. And I think actually I will start using it for my presentations in the future. So I'll just add change the title and keep everything as it is. So thanks a lot for that. So okay, so before I'll jump into the main subject of the talk, let me tell you a little bit about myself, even though you guys already presented me. So yeah, I am originally from Colombia. I did my undergraduate studies in a city called Tunja in Colombia, and then I moved to the ICTP in Italy for the diploma program in high energy cosmology and astrophysical physics. So I was 1 year in there, and then I jumped again the Atlantic to the Perimeter Institute, where I did the PSI and my PhD until 2022, and then I jumped to the PhD in Saclay to do my first postdoc. So these are like the places where I've been staying for say longer than 1 year, and also in the map you see many other flags where I visit, either giving conferences and talks, or visiting for seminars and conferences. And since this is a Latin American webinar, I think I'm gonna have to fill the whole Latin America with flags now, because there is the presence now of the talk for the Latin America. So anyway, so let me also take the opportunity to acknowledge the collaboration with many of the people that I've encountered through the years in which I've been doing research in physics. Some doing research in more particle physics than matter physics, and some are doing more research in scattering amplitudes, and my current boss, David Kosovar at the PhD, with whom we worked together. So also there was a time in Perimeter Institute where I worked a little bit with Alfredo Guevara, who you probably know. He gave a webinar as well here talking about the subject that we are gonna be talking today as well. So if you wanna also look for his talk in there, just have a look at it, and you can learn a little bit more about this exciting topic. Okay, so let me start with a small motivation. So what is it, the thing that we have in mind? So basically, the problem that we have in mind is try to understand what is the gravitational wave signal that you will get from coalescing compact objects in general relativity. And basically, this signal has a very characteristic form. So it's divided like in 3 stages. You have 2 black holes going one around each other, or in general, black hole, neutron star, or any other compact system. And at the beginning, they move sort of non-relativistically. They are very far away from each other, and the evolution is somehow like harmonic, that is not like the spiral phase. But the system is losing energy, so energy is being emitted towards infinity, and the orbits of the black holes going around each other gets smaller and smaller. And then the gravitational pulling between these two objects becomes eventually very high, and the objects don't have anything else but to merge into one object. So that's known as the merge phase. And finally, these objects radiate quasi-normal modes in sort of ring down phase. And like the first observation of gravitational wave signal was done in 2015, and now we have more than 90 events observed, and so we are transitioning from the observational to the precision frontier measurement in gravitational wave signals. And in the future, we're going to have not only the detectors that we have right now, like LIGO, Virgo, and Kagra, we're going to have many other detectors. And with many other detectors, we basically need to produce more gravitational wave templates that allow us to do data analysis. And the idea of these gravitational wave templates is that, well, on the one hand, they are very fast to evaluate, right? Because we are going to have many events showing up in the gravitational wave observatories. But also, the waves, gravitational wave template, they should keep as much information as possible about the binary system itself, right? So, the scattering amplitudes community started approaching this work in the last decade or so. I'll tell you about what are the things that we have been doing. And not only we want to just do computations and see that we can reproduce very nicely the gravitational wave signal that you were looking for, but also we want to understand a little bit better gravitational physics and the connection to quantum field theory, perhaps looking for hidden structures and symmetries that can arise that you could not see using the traditional GR approach to the binary black hole mechanics. So, but before I jump into the main subject, let me just, as a warm up, talk about Newton's first law. So this is something that we learned when we are in school, right? So said, you have a couple of objects with the masses, say M1 and M2, it can be either the Earth and the Moon. Because these objects gravitate, they attract each other, and the force of attraction between them is proportional to the masses that these objects have, and is inversely proportional to the square of their mass, right? And the first thing that we are told when people show us this law is that this is a universal law, and it's universal in the sense that it doesn't really matter where you have the Earth or the Moon or house or whatever shape this object is. The attraction only cares about the mass that is concentrated in some point, like say like a center of mass point, and nothing else. It doesn't care about the nature of the object itself. And in particular, well, there's a nice way of understanding, why such a law is universal, and it's universal because of many interesting theorems that you can prove in particle physics. So, for instance, universality of the Newton's law, it follows basically from the Weinberg-Stuff theorem. So, and the idea is that instead of try to derive this law from some more sort of first principle derivation. So basically, since this law doesn't care about the nature of the object, I can think of these objects as just point particles, right? So let's say the Earth, I'm going to represent them by some kind of scalar particle moving with momentum P1, and the Moon, I'm represented with another scalar particle moving with momentum P2. And the idea is that these particles exchange between them gravitational waves, or gravitons in general. And when the exchanging gravitons are soft, meaning that the energy carried by this graviton is much smaller than the masses of the objects, the massive momenta of the objects, then the lean order contribution in this scattering amplitude basically gives you for free the Newtonian potential, right? Because this scattering amplitude has a pole which goes like 1/q squared, and if you transform to the real space, you do the Fourier transform of that, you will get basically the Newtonian 1/r potential. The only difference in comparison with the Newton's law is that instead of considering my particles to move non-relativistically, I have allowed for them to move with arbitrary velocities, if you want. So you can recover Newton's law by basically setting the Lorentz factor to 1. And from a more sort of Lagrangian perspective, this scattering amplitude you can derive by basically considering a scalar which is minimally coupled to gravity, and you can sort of extract the Feynman rules from such a minimal coupling Lagrangian and obtain such an amplitude. So in some sense, like universality of the Newton's law is somehow analog to having a minimal coupling description of your mass of particles with gravity. So something very interesting that you see about the things that you have to put in here as the building blocks are these 3-point amplitudes. So these 3-point amplitudes are like some kind of square, and that's known in the amplitudes community as some kind of double correlations, because it's basically 2 copies of photon polarization vectors, and gravitons in 4 dimensions. You can the polarization state of gravitons in 4 dimensions. You can write them as basically 2 copies of photon states. But then this factor of 1/2 comes because you have to project out the traceless, only allow for the propagation of the traceless components of those 2 copies of the photons. That is to say, like, if instead of gravitons you have charged particles, you can also derive the electromagnetic potential for the attraction of repulsion of 2 charged particles, right? And in general, you can have them to be moving relativistic velocities. The scattering amplitude that you have to compute is exactly the same, and the only difference is that you're not going to have this factor of 1/2 for the projection of the traceless states, because the photon only has it's only propagating the vector degrees of freedom. So, but what is the message of this sort of warm-up example is that basically you can treat classical systems involving classical gravity with the tools of quantum mechanics and quantum field theory. So in general, you have to be a little bit smart on how to extract exactly the pieces that are classical, because in general, if you write a quantum field theory for describing such a system, you're going to have pieces that are quantum that you will have to discard. But like there is a procedure for doing those kind of discarding the quantum contributions. I'm not going to go very deep into that, but the idea is basically that you can use the tools of quantum mechanics to study classical systems. And that's something that we knew, since Feynman, basically. Feynman already knew how to approach gravity from a Feynman diagram point of view. And, like something that many people know, and in particular, our LIGO people also knew that, scattering amplitude people, they are very good at computing, the probability that particles interchanging certain messages scatter. And in particular, in June 2018, in the Amplitudes conference held in SLAC at that time, Alessandra Bonanno gave a very nice talk and asking scattering amplitude people, can you use the techniques that you use for computing collider observables to compute observables in gravity? In particular, she was asking, so this is a screenshot of her slides in that year, and he was asking, can you compute 2-loop scattering amplitude that will give you, like correction, 2 powers in G correction to the Newton's law? And, can you do it for objects that do not have any structure? And then can you put some kind of a structure of those objects, to mimic more real compact objects? And then the answer was like, well, in a few months, we have a couple of papers appearing saying, yeah, we can definitely do the thing that you are asking to do. So we basically want to compute the scattering amplitude between 2 massive scalars, exchanging graviton between them. And that for us is like a two-loop computation that we can more or less do with the tools that we have learned from quantum mechanics and collider physics. And an important ingredient of the computations is that basically you're gonna build higher loop amplitudes from lower tree-level building blocks. So for instance, you have like a 3-point amplitudes in there, or this thing that looks like a quantum amplitude with an additional graviton length. So the answer is yeah, we can compute it, and then people say, well, why to stop in there? You can do even higher orders in G if you like. And then many more results have appeared in the literature. So let me tell you a little bit of what is the idea of how to compute observables in classical gravity using the tools of quantum field theory. So first of all, I'm going to map the problem of two bodies going around each other in gravity to the problem in which you have two bodies scattering from each other. And they're going to be like the models for our compact objects. And then those objects are going to be exchanging graviton between them, and also can radiate graviton that eventually you can measure in a gravitational wave signal in the detector. And like the only thing that you will need if you think of this problem in a quantum mechanical wave is the following. So you want to compute how much an observable changes in this scattering problem. The only thing that you will need to know are two things. First, the initial state of your two-particle system, right? So you're going to need to know what is the initial state of these two objects in the far past. And then you will also need to know what is the unitarity evolution of these states. And if you know these two things, then you can predict compute any observables in this scattering process. And to predict the unitarity evolution of this system, well, you need to have a theory. You need to have a theory for computing scattering amplitude, right? And the inspiration from our Newtonian example was that, okay, there is going to be a region that is going to be like a far zone region in which you can model these compact objects as point particles, coupling minimally to gravity. But then eventually, when this object gets closer and closer, you're going to have wavelengths. The graviton wavelengths are going to be comparable to the sizes of the objects themselves. And then you're going to be able to tell apart the finite size structure of these objects. So you're going to have to enlarge your theory by allowing tidal operators that are going to be taking care about finite size effects. Either they can be tidal deformations of the object, like in the same way the moon deforms the waves in the ocean of the Earth, or you can also capture dissipative effects, absorption, the excitation of quasi-normal modes of these objects. And all of that you should be able to put systematically in some kind of effective field theory with some free coefficients. Those free coefficients should be able to either match them to a UV computation or to fix them by matching to data, to actual data. So this formalism comes by the name of the Kosower-Maybe and O'Connell formalism came up, and it's widely used in this scattering amplitude computation. Then you may say, well, I was not originally thinking about the scattering of black holes. I wanted to analyze two objects going one around each other. You're telling me that you are just computing scattering amplitude. Well, it doesn't matter, because actually one can analytically continue the results for the scattering scenario to the case in which those objects go one around each other. So there's a couple of prescriptions that people have used in the literature to do that continuation. Either do a Hamiltonian continuation, like very similar to the continuation that the Newtonian potential gives you, right? So basically once you have computed your scattering amplitude, you can write a Hamiltonian, and from the Hamiltonian, you can derive equations of motions, which you can solve either for bonded or unbounded orbits, right? So that's one way of doing it, and this is pretty much the way people have done to produce gravitational wave templates for doing actual data analysis in LIGO. And then there is, you know, the B2B continuation proposed very recently by Rafael Porto and Gregor Kalin, in which you map directly the observables computed in the scatter scenario to observable in the bounded orbit scenario without having to go through a Hamiltonian, which is also a gauge-dependent object. So then the lesson is like, you know, if I want to study the bounded orbit scenario, I can just study the scattering orbit scenario, and there's going to be some analytic continuation that is going to take me to the bounded orbit case. So for the remaining of the talk, I'm going to be talking mostly about the scattering scenario. So what kind of observables could you compute in the scattering process? So imagine you have two particles, you know, exchanging graviton. They come together, and then they they deviate by an angle theta, and your observable could be, you know, how big is this angle, you know, and you know, in general, solving this problem in full general relativity is very difficult to do it. You will have to solve the Einstein's equation with this configuration of sources. But we'll take advantage that we can sort of separate regions. And there is a region in which, you know, these objects are very small as compared to the separation between the two. Basically, you know, the sizes of those objects are much smaller than the impact parameter. And then you can do the computation of that scattering angle order by order in GM over V. So this expansion is what is called the post-Minkowskian expansion, and basically, you know, allows you to, you know, compute a higher order observable basically from higher loop amplitudes, you know, for say scalar or spinning particle exchanging graviton between them. So an analogous expansion can be done if these objects have a spin. So if they have a spin, you can also allow for the spin of the black hole to be for the spin ring radius of these objects to be much smaller than the separation between the two, and do a computation in what is called the spin multiple expansion. So basically expansion powers of A over B. But then you will say, but wait, like you are telling me that you are computing observables for classical physics, and then you're telling me that you have to compute loop diagrams. And that doesn't resonate, right? Because if you remember your courses of quantum field theory, they will tell you that, you know, tree level is classical and then loops is quantum, right? So the way in which you reintroduce the H-bar counting in your QFT computations is, you know, by rescaling the couplings with H-bar. So basically, you know, if you rescale G, you know, the post-Minkowskian parameter will, you know, at higher and higher orders in the loop expansion, it's going to be more and more quantum, right? So, but the idea is that, you know, instead of thinking of Q, well, Q is like the conjugate of this impact parameter. Instead of thinking of Q as a transfer momenta, you're going to have to think of Q as a wave number. So basically, it's writing the wave number scaled with H bar, and then the post-Minkowskian parameter, if you scale G with minus H bar, Q is also going to be scaling with H bar in such a way that this combination GMQ remains always of order H bar to the 0. So basically telling you that's the way in which you will get classical contribution from loop computations. So the same can be done with spin. So spin can also be scaled with H bar, and the combination of spin times momentum transfer are going to be of order H bar to the 0. So then, you know, what you have to do is basically to compute observable order by order in G. And in general, this is becomes more and more complicated, right? So you're going to have a three-level exchanging and then loop exchanging between the gravitons, between the massive particles. And the computations get more and more difficult, but there are very, 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 you know, like bold people that do those computations. And in this plot, we're sort of summarizing what is the state of the art in the computation of this, say, observable for bounded and unbounded and bounded scenarios. So let me tell you a little bit about that. So in this plot, we can see the scattering angle as a function of the angular momentum of the system. So basically, as a function of the impact parameter, roughly speaking. And it's the scattering angle that you will get, including higher order corrections in the post-Minkowskian expansion. So there is the first dotted line is the 1 p.m. computation, in which you have only the graviton exchange diagram, and then you go higher orders in the loop expansion. And the black dots in here are the result that you will get if you will solve the Einstein field equations using numerical relativity. So for us, that's sort of like the true answer. And one thing that you see is that this series gets better and better. The higher you go in the post-Minkowskian expansion, the better you approach the actual solution to the Einstein field equation. But if you look at the Dutch lines, they don't go very close to the actual solution of general relativity. Well, the reason is that you can do a little bit better and resum certain contributions in the post-Minkowskian expansion. Like, for instance, you can resum the geodesic motion, which has information about all orders in G. The geodesic motion is very easy to compute in general relativity. And when you on top of the post-Minkowskian contribution that given by the Dutch line, you also introduce information in your effective Hamiltonian to resum the geodesic motion, then you get the result for the solid lines, and the solid lines get much closer to the actual solution given by the numerical relativity. So that's a sign that maybe we are doing things correctly. There are still some debates about this kind of plots, but roughly speaking, that's the idea of computing observable using amplitude techniques. So, but that's for the unbounded case. Now we are interested to study the bounded orbit system. And as I told you, well, there is a map that takes you from the unbounded to the bounded. So for instance, you can compute the binding energy of the binary system as a function of, basically the velocity, or, how many cycles you have before these objects merge. And you see that actually, the black dashed line is the solution that we get from numerical relativity. You see that, including higher PN solutions, like this red line, they get more or less good agreement with numerical relativity, even very close to merge. So you're basically pushing the result that were supposed to be valid when these objects are very far away from each other, but somehow they describe, roughly speaking, roughly well the dynamics of the system, even in the case in which those compact objects get closer to merge into a single object. And of course, after they merge, well, the solutions, you cannot trust them anymore. They deviate from the numerical relativity because you have to use the numerical solutions in the phase in which these objects have collapsed to each other. But the message is that since we are doing an analytic computation, we can evaluate these things basically instantaneously. So in the future, when we have gravitational waves showing up with high frequency, so we're going to have like many events happen all the time, and we're going to need gravitational wave templates that you can evaluate very fast to do much filtering. And this analytic tool gives us a way to evaluate the gravitational wave templates very, very fast. So this is the state of the art in the computation of observables in the binary black hole problem. So I was mostly telling you about the higher order corrections in the post-Minkowskian expansion, which is all of these all of these horizontal lines shown in this table. And you can see these are basically the corrections to the Newtonian potential higher orders in G, but resuming all orders in velocity. And the state of the art up to the date of this talk is the 5 post-Minkowskian order, basically like a for loop computation, but it's a for loop only including the so-called 1SF sector. So one cell force in which you basically don't see basically you're considering one object which is very big and the other object is very, very small. So, but that, in the past, so this is like the modern computation in which you do post-Minkowskian expansion and resume velocities. In the past, people were following a different approach. And the approach was that given by the post-Newtonian approach. So you roughly speaking compute diagrams very similar to the diagrams that you get in the post-Minkowskian computation, but the Feynman rules that you use for building up those diagrams, you expand in V and you start include higher orders in velocity, depending on what order in the post-Newtonian expansion you are interested in, right? So the reason people started expanding in velocity was because they were also thinking directly on the bounded orbit scenario. And in the bounded orbit scenario, higher powers of G are related to higher powers of velocity by the virial theorem. So that's the reason you can truncate a certain order in G by truncating in the velocity expansion as well. So the state of the art in the post-Newtonian direction is the 5pn, and there's actually something very interesting happened at this order, because this is the order at which you will see the objects not as point particles, but actually objects with some finite size structure. So that is to say, all of the results before the 5pn, they basically can be derived assuming that these objects are point particles. So really like some similar to the universality that you saw in the Newton's law, in which you can think of those objects basically as point particles. Up to here, up to lower PN orders, you don't really care about the finite size structure of those objects. And actually, this finite size structure start to show up with, say, 10 powers of the velocity of them. So that basically means that to observe those finite size effects, you will have to go to very high frequency part of the band of the detector, and actually those tidal effects show up here, and they cannot be captured by LIGO so far. So these are like static tidal deformation, and are supposed to be non-zero for neutron stars. They're supposed to be zero for black holes, and the thing is that the gravitational wave signals observed by LIGO for the coalescing of neutron stars, if you look only at the gravitational wave signal, you wouldn't be able to tell whether this was a neutron star or a black hole, anything, because so far you cannot measure by LIGO these tidal deformabilities of the objects, right? So if you didn't have the electromagnetic counterpart for these gravitational wave events caused by neutron star, you wouldn't really be able to tell where those were neutron stars or black hole or any other kind of compact object. So, okay, so that's more or less the state of the art in the computation when you think of these objects as, scalar particles. So roughly speaking, you have in mind the Schwarzschild black holes because they don't have any rotation in them. And actually, most of the work that I've been doing is not in the Schwarzschild sector, but actually in the case in which the objects rotate. So meaning when you have Kerr black holes. So this motivates actually the title of the talk. How do you think of Kerr black holes as elementary particles of with spin? So for Schwarzschild black hole, basically you can think of them as elementary particles without any spin. And now we're gonna see how the analog computation go in the case in which you have a spin. So the simplest kind of object that you can have is the isolated Kerr black hole itself, right? Kerr black hole sitting there, nothing is perturbing it. You know that geometry is described by the Kerr metric. So this is the Kerr metric. You have two horizons, an inner and an outer horizon, which are the solution to this polynomial equation. And those horizons are real as long as the spin parameter of the Kerr black hole, meaning the parameter that characterizes how fast the black hole rotates, is smaller or equal to 1. So that's the case in which you will have an actual black hole and not a black hole without a horizon. So we want to observe this black hole from very, very far away. So from very, very far away, you expect the black hole to look basically like a point particle. So if you take your Kerr metric and then extract the Lie order in GM over R, so GM is the size of the black hole and R is, you are sitting very, very far away, you're basically gonna see the black hole as point particle. But the nice thing about having a spin is that you can introduce back the spin effects and you can actually resum them. So you can do also a spin multiple expansion in powers of A over G, in powers of A over R. And if you do that, you take your Kerr metric, take leading order in GM over R, but all orders in A over R, you will find that the metric, well, this object becomes basically the metric of a naked ring singularity, and it has this exponentiated form. So it's like a sort of shift, like a complex shift of the Newtonian potential. So that shift is actually known as the Newman-Janis trick, which allows you to recover, the Kerr solution from the Schwarzschild solution. So, but this is a very nice object. Like if you look at it, it basically tells you that the spin multiple moments of the Kerr black hole, they are kind of simple in the sense that they exponentiate. So they look like an exponential. And actually this exponentiation is very particular for Kerr and not any other kind of objects. So if you have neutron stars rotating, you're gonna have to be able to write a metric for such a rotating object. But if you try to resum the spin effect for such a neutron stars, those do not exponentiate in a nice way as the one for the Kerr black hole. So they are somehow special. They're special because you can describe the same object by a particle, a spinning particle emitting a gravitational wave. So basically, if you take the Fourier transform of this object, it basically looks just like this exponential. And this is, as I'm telling, this amplitude you can fix it by pure Lorentz covariance. So you have a particle of spin S going in and then going out, and at infinite spin, in the limit of infinite spin, this amplitude becomes exactly the same exponential as the exponential for the Kerr metric. So that's very nice. And then we say, okay, but how about when you have black holes going around each other, these black holes, they are not just alone; they are perturbed by the gravitational field created by the other object. So then there has to be more complicated objects that describe the dynamics of black holes going around each other. So the next object that you could consider is like something that instead of looking like a 3-point amplitude, looks, roughly speaking, like a 4-point amplitude, so an additional gravitational. And this is known as the Compton amplitude. And the claim basically is that this amplitude is equivalent to describing the linear perturbations of a Kerr black hole when you send, say, a plane wave perturb this black hole, and then it gets scattered because of the gravitational potential created by this object. So in the remaining of the talk, we're gonna describe study a little bit of what this amplitude look like. And to extract such an amplitude, well, you have to extract you have to solve the solution, the equations of that tell you how these perturbations of the Kerr black hole evolve. So these are known as the Teukolsky equation. And these differential equations are in general very complicated differential equations because actually they are of Hoyne type. So it's like a very fancy name to tell basically that the closed form solution to this differential equation has remained an open problem for the last 200 years. So we are not going to be able to solve the Hoyne differential equation or the Teukolsky equation exactly unless we do some approximation, like like long wavelength approximations and stuff like that, which allow us to extract the analytical solutions to the Teukolsky equation in certain regions. So I'm not going to tell you what the Teukolsky equation looked like. I'm going to tell you what the solution of the Teukolsky equation looked like. And in particular, there is a very nice connection of, the equation deriving the equation in black hole perturbation theory to equations that show up in other fields of physics, like conformal field theories and gauge theory. So let me walk you through what is written here. So just gonna be doing the following. So I have my black hole here. I will send the wave. The wave gets scattered, and at infinity, I'm gonna compute the fluxes of energy that goes to infinity, and I'm gonna normalize the fluxes of energy to the incoming flux. That's gonna give me like a differential cross section, like scattered differential cross section. Then I'll take sort of the square root of that differential cross section, which allow me to define like scattering amplitude. So that scattering amplitude you can write basically from knowing the phase shift. So the phase shift is the solution to the Teukolsky equation, and then the scattering amplitude are going to be given by partial waves of this phase shift. So, but the phase shift is the important object. And the solution it has a very complicated structure, but you can, first thing that you can observe is that you can split the solution into pieces. The red piece, which we call the far zone piece, and then the blue piece, which we call the near zone piece. And basically the red piece it tells you, what the scattering amplitude will tell about the object. So in the far zone region, the object look basically like a point particle, and this object will take care of, the dynamics of the point particle. But eventually, you're going to be able to also see near zone effects, which basically tell you, the finite size structure of these objects. So in particular, this is function of this kappa function, which is called the black hole tidal response function. We're mostly talking about black holes. And this tidal response function is very interesting because it captures physics happening very near the horizon of the black hole. And to be a little bit fancy, I have written the solutions in terms of these objects showing up in conformal field theories and gauge theory. So in particular, there is a resumed form in this exponential of this f function, which people know as the Nekrasov-Chodelvili function. It's a very nice function that has very nice properties that I'm not going to be able to discuss. But knowing those properties allows us to prove several facts about the solution itself. And there is a dictionary that relates, gauge theory parameters to the black hole perturbation theory parameters, such as like spin of the black hole or the post-Minkowskian parameter, and A, which is roughly speaking like the angular momentum of these partial waves. So what does the near zone physics solution look like? Well, it has several properties. So the first one, as I was telling you, that captures the dynamics in which, for which the black hole looks like point particle. You can prove using the properties of this Nekrasov function that the far zone solutions are purely conservative. So basically, there's no dissipation of energy in the scattering process. And also, in particular, there is not the appearance of the parameter of the horizon of the black hole never appears in there. So the solutions are always polynomial in the spin parameter, which basically aligns very nicely with the spin multiple expansion in your effective field theory description of these objects. And finally, if you did any black hole perturbation theory solutions in the past, you know that you can also solve the Teukolsky equation by allowing the infinite sums of the MST coefficients, and this infinite sum nicely resolve into this exponential of the Nekrasov function. The near zone, on the other hand, as I was telling you, is a function of the tidal response function, and it's a very complicated function. It is non-analytic in the post-Minkowskian expansion. Basically means that you're going to start to encounter logarithms, and those logarithms have a very interesting physics happening there. And but unlike the far zone solution, the near zone solution contains both conservative and dissipative pieces. In particular, it captures, how much energy and angular momentum can be crossing the horizon of the black hole. So it's captured basically by this eta parameter. And they also, this Taylor response function allows us to write a like exact quantization condition for the quasi-normal modes, but we're not going to talk about quasi-normal modes here. So let's continue. So, okay, so we have the solution to the Teukolsky equation, and I want to write scattering amplitude similar to this 3-point amplitude, but now for the quantum amplitude. So basically means that I'm going to have to do those infinite sums. So that's something that can be done very easily. So the quantum amplitude, the 3-level contributions, you're going to have like a far zone contribution coming from the red pieces in the phase shift, but then also you're going to have like a near zone contribution coming from the tidal response function of the black hole. And in particular, this scattering amplitude, it looks very similar to the exponential that we have for the isolated Kerr metric. So you have an analogous exponential for that case. But the difference is that this exponential is only valid up to 4th order in the expansion in A. So after the 4th order, you're gonna be able to write a contact deformation for this exponential. And in particular, any contact deformation that you write at 4th order in spin vanishes. And the reason is that all of those contact deformation at 4th order in spin are proportional to 2 powers of the tidal field that created this, these perturbations of the object. And those tidal fields are of static nature and therefore vanishes. So that's the sort of like an on-shell way of saying, the static love numbers for the Kerr black hole vanish. At 5th order in spin, you're going to be able to write a contact term that looks that does not vanish, and there are terms in your effective action that are proportional, say, to 2 copies of tidal fields, right? But those tidal fields come with, in general, with derivatives. So these are dynamical tidal deformations, and in general, they do not vanish for black holes. So that's for the, say, like the conservative part, meaning the part that didn't have like the absorption included in there. But as I was telling you, the black hole solution also have absorption. So the explicit form of this coefficient are basically fixed by the Teukolsky solution. Just some numbers that take care about the finite size structure of the object itself. So you see that these are not just rational numbers, as the usual numbers that you will find in this exponential. They come with non-rational numbers, and those non-rational numbers are characteristic of telling you, this object has some finite size structure. So for the dissipative part, meaning the part in which knows that the black hole can also absorb energy and angular momentum down the horizon, you will have an analogous contribution and spin to the 4. These couple of numbers are fixed by the black hole solutions. And this is very reminiscent of the way people model absorption in our effective field theories approaches to the problem, because basically, since these are like contact terms, they also look like localized degrees of freedoms on the object, so like on the world. So we have a 3-point amplitude, we have quantum amplitudes, and you may say, okay, what is this useful for? Like, at the beginning, we were interested to study the binary black hole problem, and now we were studying like only one object. Well, the reason these objects are interesting is because, as I said at the beginning, you can use those as building blocks to compute correction to higher post-Minkowskian observables in the two-array problem. So you can either compute observables for the conservative observable, like the redshift or precession frequencies, and in general, the way of doing is basically you write an effective Hamiltonian, and from that effective Hamiltonian, you solve the equation motion for the system and get solution for that. And I don't want to focus too much in this talk about the conservative results. They are big, I don't know, they are not very illuminating. This is the correction, say, for the 1/4 redshift at 5th order in spin multiple expansion. And in particular, they come with these free coefficients F60, G60, and so on and so forth, which you can fix from the solutions of the Teukolsky equation. Nice thing about this observable, though, is that you can do like a resummation of the eccentricity. So basically, so the observable is valid where you have objects going one around each other or objects scattering from each other. The one that I wanted to discuss is these are observables that people don't look too much because these effects are very difficult to observe in gravitational wave systems, but nevertheless, it's very interesting to understand the dynamics happening around the horizon of the black holes. So in particular, we're gonna discuss about dissipation, so absorption. So you can think of this line as, say, a charge of a Kerr black hole that is moving in the gravitational field created by this other object. And, if the wavelength of this exchange gravity between these two guys is small enough so that it can be absorbed by the black hole will absorb it and then will change its mass. So the mass of the incoming and the outgoing guy are going to be, in general, different. The angular momentum of the object can change too, but I'm going to be talking mostly about the changes in mass. So one of the observables that you can compute was, how much the black hole changes mass due to the absorption of the gravitational energy and angular momentum carried by the gravitational field created by the big object. And that's basically telling you, you have to compute the expectation value of the energy carried by this messenger. And the computation is technical, but there are some interesting things happening when you look at the results. So the first thing that you'll see is that, if you have a Churchill black hole moving into this external gravitational field, the mass of the Churchill black hole will change by this factor. So it's a relativistic result, if you like. So any order in velocity, but it's leading order in G. And this is showing already 7 powers of the Newton constant. So that basically means that it's very, very, very small in the post-Minkowskian expansion. So I was telling you the tidal deformabilities show up at 5 pn order. These guys show a little bit higher in the PN expansion than the tidal deformability. So far, we are not even able to measure tidal deformation for objects in the LIGO detector, for instance. There is not hope that we are going to be measuring these changes in masses of the black hole, but nevertheless, they are interested to study because this guy goes to G2 as G to the 7, but for spinning black holes, there is actually an enhancement, and this enhancement happens because the black hole has spin. So the change in the mass of a Kerr black hole due to the absorption of gravitational energy and angular momentum carried by these objects will show up at order G to the 6, still not low enough to be observed by a gravitational wave detector, but it's a little bit better. And something interesting about this formula is that if you take to 0 the spin parameter of the black hole, you will get 0 instead of getting the Schwarzschild result. And the reason is that these objects are discontinuous in the post-Minkowskian expansion. So to recover the Schwarzschild result, you will have to go to the Kerr result as one higher order in G, and meaning G to the 7, and then take the spinless limit to be able to see the Schwarzschild result. So the right-hand side of these equations can be understood in a sort of more like a gravitational language. You can understand as the right-hand side as induced mass quadruple moments on the object by the gravitational field of the big object. So this is the epsilon is the gravitational field created by the big object, and it induces some tidal deformabilities on the black hole due to the absorption of gravitational waves. So you see then that the philosophy was basically, like try to use lower level building blocks to study observables in gravity. You can do this systematically, compute any other kind of observables in similar ways. And today I'm gonna stop in here. So let me just summarize what we learned today. So sort of give you a glimpse of how these new on-shell techniques are used to study the binary black hole problem in general relativity, both for bounded or unbounded or bounded systems. We're also interested in modeling spin effects and how to think of Kerr black holes and finite size effects as those obtained from the solution of the Teukolsky equation. Show you how to compute observables such as the changing mass of a black hole by absorption of energy and angular momentum, and told you a little bit about the state of the art in the problem. So lastly, before I conclude, let me tell you that this is a very recent community. They have been gathering for the last sort of 10 years or so in a conference happening every December. It's called the QC Miss Gravity Conference. This year is going to be happening in Taiwan. But for TV people in Latin America, the next conference is going to be organized in Sao Paulo at the ICTP Savior. So if you are interested in knowing a little bit more about this community and these new techniques to approach the gravitational binary black hole problem, well, try to apply for this conference or schools in there. So thanks a lot for your attention.
Thank you very much, Fabian, for your nice webinar. Very nice, the Modelo 3D in your slide. So
yeah.
it's very from Giorgio Di Russo.
I just put Porro.
Very nice. Okay, for the people that are following the transmission, you can write questions for Fabian here in the chat in the live transmission in the right hand side of the page. So just to remind to the people also that that to follow us in the social network and to subscribe to the YouTube channel, because it's very important, because you are gonna get the notification when each time that we have a new webinar. So maybe we can start with some questions. I don't know, from the people here in the audience. Alejandro has a question for Fabian.
Thank you, Fabian, for this wonderful overview and the state of the art of this. I can imagine it's a pretty messy business as well. So let me start. I have many questions, but maybe just to limit it to some of those and then going backwards in your talk. So ideally, if you say like, okay, we start with this two-body problem, we want to analyze that, but then we move to the single body that is perturbed a la Teukolsky. So the idea would be like we can somehow stitch these two results. So in some sense, you get results of the binary evolving, somehow it merges. I'm not sure you can get information of the merger through this approach, and then connect to what you are discussing here with the Teukolsky equation, or how is in this community the whole problem? And let me ask the question precisely, is because there's a lot of calculation here, and one of the things you mentioned is very nice because it's analytical and you can just instantaneously compute it. But now the question is, at some point for us astrophysicists to use it, you might want to build it together, right? So can you comment on that again, please?
Yes. So basically, the idea is that the scattering amplitudes approach allows you to treat the problem where you can where you can use perturbation theory. So that's basically the region, the initial region that it's called the inspiral region, in which the objects are separated well enough. But I was showing that the result that you will get using this perturbative approach, you can push them very close to the merge phase. But at the merge phase, you cannot do perturbation theory. So in this phase, you will have to solve the Einstein's equation numerically. And in the last stage, well, you can use black hole perturbation theory. So what is done in the pipelines for doing data analysis is that you put together all of these three stages. So you put the analytical stage in the first part of the waveform, and then you have the numerical solution from numerical relativity to give you the other part of the waveform, and finally the one coming from black hole perturbation theory. So there is some sort of semi-analytical final template that you build for doing actual data analysis. So for us, we have been mostly concerned about the inspiral region, where we understand very well how to do perturbation theory. But actually, there are some people already thinking of how you can model from an on-shell approach what is, the merge phase will look like. If you think of say, because the merge phase, roughly speaking, is like, you have two particles coming in, and then they merge into another one, and then they emit a gravitational wave. So it's like a fourth particle. And there is a recent paper by Yuting-Wan and collaborators in which they propose, a way on trying to approach the merge phase, but it's still a little bit too far from us. For the moment, the results that we have for the inspiral phase are good enough and still challenging.
And just with that, in principle, this approach, you should be able to push it closer to the merger, right? Because as opposed to let's say the post-Newtonian, which, well, yeah, it will break as soon as like the velocities will be high. You can correct it or do like the effective one problem. But here, in principle, you can really, I see, yeah. So actually, even though it's perturbative, you can actually get quite close, right? Yes.
Exactly. That was what I was trying to tell in this plot. You know the different perturbative solutions, but actually those solutions, if you push them very, to the extreme where the black holes are almost merging, they're more or less, good as compared to the general to numerical relativity results. But still it might depend on the system itself, but at least for the inspiral phase is good enough.
Thank you, Fabian. And then, so in these expressions that you show, you always have M1 and M2, and they don't have to be comparable mass black holes. And I can imagine here this comparison is done because LIGO observes mainly comparable mass black holes. But in principle, is there any limitation if you want to do intermediate mass black hole, or I want to take M2 to be smaller, and then these expressions will still hold and work like that? Because as you know, there's also like the gravitational self-force approach to another type of perturbation where there is a small one, the M-ray scenario. So can we export any of this technology to the stream mass ratios model?
Yeah. So like the nice thing about the result that I presented so far is that since they are perturbative in this region, sort of the post-Minkowskian approximation also captured part of the self-force approximation.
Okay.
And though orders in the post-Minkowskian approximation, you can only get leading in the mass ratio correction. So basically that means that the lower post-Minkowskian result, you can use them for comparable sizes, masses. If you want to go to higher orders in the mass ratio, definitely this approach is not going to be enough. Because basically one of the reasons is that, well, on the one hand, you're sort of going to have to resound the geodesic motion itself. But also you're going to have to take into account the back reaction of the object, of the small object itself, and this back reaction on the small object is something very tricky to include models, and basically there are a lot of challenges in trying to include that back reaction on the small object. That's why the state-of-the-art result so far, it's 5 p.m. Say 4 loops, but only the one sector is known. Like higher.
Now I understand.
OSF contributions are still very, very tricky to include. So the answer, the short answer is like it's a big challenge to the large mass.
And then just last quick question. So I in the last part of your talk, I got confused a little bit. So you in addition to this perturbation, maybe I misunderstood this part. Are you also, for certain results in the spin case, you have to assume the spin also perturbatively? And if so, I didn't quite get.
Yes.
So how in those expressions, like the spin, to which order do I get it, or like it wasn't clear to me. Can you explain that again, please?
So what we do is the following. So basically, okay, we can do both a post-Minkowskian expansion, meaning powers in G and R, but also you can do a spin multiple expansion, which expansion powers of spin parameter over R. And you can do, say, leading order in the post-Minkowskian expansion, but all orders in the spin multiple expansion if you want.
I
Right? So
see.
this exponential resumes all orders in spin multiple expansion, but they are leading order in PM, right?
I see. I got it. Yeah. Okay.
But so that's like for the isolated black hole, like resuming the spin multiple moments of the objects is something very easy to do. When you perturb the black hole, resuming the spin multiple moments is very difficult. And the reason is that when you perturb the object, at some point, the spin multiple moments are going to be mixed with the tidal deformations of the objects. Then separating and including all of these effects is something very, very difficult. So the result that I show for the solutions of the Teukolsky equation when the object is perturbed are I stop at the fifth order spin multiple expansion. So meaning all of these contact terms that I include in this quantum amplitude, they are valid up to order spin to the fifth. And then if you want to go higher order spin multiple expansion, you have to understand what is the interplay between the spin multiple moments, finite size effects, and the tidal deformability of the object, which is something very challenging to understand.
I see. Sorry, but then you stop here is because you need to go like in the same order spin multiple as well as the post-Minkowskian or something like that. So you stop here at 5.
In principle, you can consider the two expansions to be independent from each other.
I see.
And but then the challenge is not on the computation. You can do it, right? It's not very difficult. You can just include one higher order in A omega if you like. But the difficulty is to understand what is the meaning of these different terms. So, for instance, the spin to the fourth, the only deformation that you can put are like static tidal deformation, and they get set to 0. Like you understand that they have to be 0 because the log numbers of Kerr black hole are 0. And then the next order you have like dynamical deformation, and then at the next order
But that's something you put by hand. Sorry, is that something you know and then you or is because they ended up being 0?
No. So let's say you can write like an effective model for what the way these spin multiple moments scatter of these gravitons, right? And in your effective model, the only operator that you can put in there are, say, a spin to the fourth, the deformations of this guy. The only operator that you can put in there are proportional to the square of the tidal fields. So the static tidal fields, and then you're gonna have some powers of spin going in there with a free coefficient. And then you match that free coefficient to whatever the UV solution tells you, well, the Teukolsky equation. And the Teukolsky equation tells you that those coefficients should be 0. So you understand, okay, that this is just the vanishing of the.
Okay.
And then higher orders is a little bit more complicated because there is more operators that you can put in there, and then you have to start interpreting what they look like. And then also at higher order, you have a mix the conservative effect with the absorptive effects. So it's a very intricate problem, and the reason basically we stop here is because we want to understand how to disentangle all of these effects, and it's a little bit messy to do it this way.
Gotcha. Thank you, Fabian. Thank you for the nice webinar.
Thanks.
Okay, we have time just for I guess one more question because of the sake of the time. So I don't know if Joel has a question. I mean, from YouTube they are saying hi to Fabian, Henry. So hi to Henry. So I have a very kind of naive question, or I don't know if it is so naive because sometimes happens that it's a complicated question. But with all the formalism that you explained to us very, very nicely, it can be used also to try to see effects in primordial black hole scattering in the early universe, let's say, because at the end you could model, let's say, the interaction of a gas of black holes, if we think that we have in this early stage of the universe in which they are popping out a lot of small mass black holes scattered one to each other, and not considering like in standard cosmology that is just in inert gas of black hole. I don't know if it is.
Well, that's a problem I haven't actually thought myself of, but I mean, the approach basically tells you that as long as you have some kind of perturbative parameter with which you can play, Like for instance, in our case, the perturbative parameter was the sizes of the objects divided by the separation of the objects. Then you can sort of do perturbation theory and compute observables in this way. In the primordial black hole scenario, I'm not very familiar to what the dynamics of the whole system look like, so I'll have to think a little bit. But you know, the answer is like if you have some kind of perturbative parameter with which you can play off, then there might be a way of approaching the problem in a more modern on-shell approach.
Yeah, because I was thinking also on the, as how it's called, in the stochastic noise in the gravitational waves, let's say. I mean, of course, it cannot be observed yet with the current interferometers, but maybe can be also explained with this formalism, the shape of the spectrum of this noise.
Well, yeah, that's something very, very interesting that we take a look at. I have no idea what the answer will be, but I will be very, very eager to try to check on that and see.
Yeah, for that reason I said that was a naive question because no, and the other question because it's also completely different of this one of the primordial black hole, but because usually when people study black hole, they have the Schwarzschild, the Kerr, and also the one that is with its charged black hole. Is it also possible to incorporate this type of black hole?
Definitely, yeah. Like the Teukolsky equation that you write, in which you have also charged black hole, is also of point type. And the solutions are very similar. Like this formula that I show for the solution of the Teukolsky equation is there is an analogous formula in which you allow for these masses to be also function not just of the spin parameter of the black hole, but also in the charges. So if you have a Kerr-Neumann black hole, for instance, so you can definitely do that. And then the way you're going to understand, scattering processes are that, in addition for your objects to exchange graviton between themselves, they can also exchange photons or, like any other messenger that couples to the charge. Okay. So yeah, that can be definitely done as well.
Yeah, nice.
But actually, using this technology, I mean, there is many exotic objects like fastballs and the D-branes collection of D-branes that you can perturb, and those geometries will give you a differential equation which is very similar to the Teukolsky differential equation. So the solutions are also the same. So in principle, there is room to do more phenomenological waveform models considering more exotic compact objects. But how where the effects of having more exotic compact objects you will be able to tell apart in a gravitational wave observatory, that's a different story.
Okay, thank you. So I guess, from YouTube, I guess there were no questions. No question, just the hi from Henry. But so we are gonna finish here the transmission. For all the people that follow the webinar from Fabian, was a pleasure to have you here. Also to Fabian to talk about these nice aspects of gravity and how to use QFT to compute the scattering amplitude. And of course, for all the people that follow the webinars, in 2 weeks from now, we have the webinar from CoolDeca. So all of you are invited to attend to the live transmission. So thank you all, and we see us in 2 weeks for another Latin American webinar on physics.
Thank you, Fabian.
Thanks.